In order to balance this equation, I have to have as many hydrogens on the left as I have on the right. I've got the same number right now. To get the number of oxygens to be the same, I can't put a subscript here. That would be changing the formula for water. It wouldn't be water anymore if I put a subscript 2 there. It'd be hydrogen peroxide, and we're not changing it. We're using the same thing. So we have 2 oxygens, I've got to put a 2 here. But that changed the number of hydrogens. So to balance out the number of hydrogens, I need a 2 here. Okay? And that's the basic idea behind balancing an equation. Okay? But some equations are far more complex than that. Okay, so balance this equation. All right, well, let's see. On this side of the equation, I have 2 carbons. To have 2, I'll put a 2 here. That also gives me 4 oxygens, so I guess I'll put a 4 here. And I need 6 of these. I'll need a 3 here. But that means I now have, oh, that's going to mess up the number of oxygens, isn't it? Right now, I've got 4 oxygens here and 3 here. That's 7, right? So how do I get 7 of these? I can't. If I put a 7 here, that'll give me 14, right? Well, let's see. That means I've got to go back and change this to 6. And this to 4, and this to 2. Okay, well, I kind of know where things are going. You can imagine some of these get pretty complex. This is a simple equation. Okay, so we're going to use something called an atom inventory. All right, did everybody get this by inspection?
I got a 5 in front of the O2 and a 2 in front of the CO2.
Well, let's see. If you put a let's use a different color here to see how that works out. You had a 5 here and a 2 here. Okay, so that gave me 4, and that would be 6, and that would work out, wouldn't it? That could balance it out, right? Did I miss it? Did I miss anything? So you didn't have anything here. There'd be 6 of those.
Well, I had a 2 in front of there. And then
2?
A 6 in front of the H2O.
A 6 in front of the H2O, which means I've got 2 times 2 is 4 plus 6 is 10, and that would give me 10. That would work. Okay, that would also balance it out. We're going to use what's called an atom inventory when you balance equations. So let's look at, say, C4H, let's see, 10, O2, CO2, and H2O. Okay? So it doesn't matter what kind of equation, how simple or how hard it is, I want you to write an atom inventory every time we do an equation. Okay? And to do an atom inventory, you want a vertical line underneath the arrow. You want a vertical line somewhere over here to the left. And you want to write the elements vertically like this. Okay? And then you want to put horizontal lines between the element symbols. Okay? So what we're going to do is we're going to count everything that we have on the left and on the right. So this is just an organization tool. All right? It's called an atom inventory. And it's it's a really good tool for balancing equations, and you might not need it after this class for a lot of the classes, chemistry classes you take, but when you get to the complex things, if you don't use it, at least you'll have it. You know, if you practice it, you're going to have it. It'll be a tool you can use. But in this class, every time you balance an equation, you've got to have it. So let's see, we've got 4 carbons at the moment. We've got 10 hydrogens on the left at the moment and 2 oxygens on the left. On the right, we've got 1 carbon and 2 hydrogens and 3 oxygens. Okay? And then we'll go through and just start putting coefficients where we think we need them. I suggest, and this is a tip to help you balance equations. Anytime you're balancing equations that contain oxygen, balance the oxygen last. Doesn't mean you have to list it last, but you should balance it last. Okay? And any equation that contains hydrogen, balance the hydrogen next to last. Okay? So oxygen last and hydrogen next to last. That will serve you well if you will do it that way. All right, so I've got 4 carbons on the left. In order to get 4 carbons on the right, I need a coefficient 4. I can't change the formula. Once the formula has been balanced, we leave it alone. By putting that 4 there, that changes the number of carbons I have on the right, so I'm going to cancel out carbons and oxygens. And this is another little tip when using an atom inventory. When you put a coefficient in front of some species, these 4 things here, these symbols of these formulas, those are called species. When you put a coefficient in front of a species, always immediately mark those numbers, corresponding numbers out, so you won't forget to go back and do that. Some formulas have 3 and 4 different elements in them, and if you'll mark them out right away, you won't forget to balance them, and it'll save you some trouble later on when you can't get the equation to balance, you can't figure out why, and you're pulling your hair out. Well, just if you'd marked them out to start with, you'd have been in good shape. Okay, so always mark out the numbers you have in the atom inventory immediately when you put a coefficient in the equation. Okay, that way you won't forget to go back and balance things. So that gives me 4 carbons, and when I have more than one place with the same element, like I've got oxygens in 2 places, it's always a good idea. I'm not going to give you points for it or count off for it if you don't do it, but it's always a good idea to sort of add them up as you go along. Because when you're doing these things over and over again, trust me, I've been doing this for a long time, just keeping up with the math makes your life a lot easier. A lot of times when you make a mistake and you can't figure out where it is, you look back at where you did something really simple like addition, you missed something. You know, having it written down somewhere helps you to solve problems a lot faster. So I want to write down that I have 8 plus 1, and that gives me 9, so I'll put a 9 here. Okay? So I'm going to save oxygen for last. I'm going to balance the hydrogens now. I'm going to put a 5 here. And immediately I'm going to put a line through these 2 numbers because those 2 numbers will be affected by that coefficient. That coefficient changes the number of hydrogens and it changes the number of oxygens as well. Okay? So now I have 10 hydrogens and I'm going to add up the number of oxygens I have. So I've got 4 times 2, that's 8. Plus 5, so I have 13 oxygens at the moment. Okay? All right, so everything works out except the oxygen. And when you have a situation like this where you have an odd number on one side that can only be, well, an odd number on one side and an even number on the other, and this side can only be even. I can't have anything other than even numbers of oxygens here because I've got a subscript 2 here. So for that, in that case, then you want to make sure that you want to fix this so that the number of oxygens are even on this side. They have to be. Otherwise, you can't balance the equation. So when that happens, then you want to go through and put coefficients, change the coefficients, multiply all the coefficients by 2 so that you have an even number of everything in there. Okay, so if I change this from 1 to 2, and this from 4 to 8, and this from 5 to 10, I've multiplied everything by 2. I can very quickly go through and change the number of carbons to 8, number of hydrogens to 20, the number of carbons and oxygens and hydrogens over here, I'm going to double all those by those coefficients. That's 8 and 20 and 26. Now I can put a coefficient, I pretty clearly see I put a coefficient 13 there to give me a 26. All right, that's an atom inventory. Pretty simple little tool, but it can sure save you a lot of headaches later on, especially under the stress of a quiz or a test. Okay, you kind of make sure you got it right. All right, get used to using it, get in the practice of using it, and when the time comes and you need it, you'll have it. Got it? Every time you do an equation for me, got to have an atom inventory. Got it? All right. So a couple of things let's go through here with these equations I've shown you so far. One thing is that hydrogen and oxygen under normal conditions are gases. And when we do equations here, we need to list their physical state. So this is a gas. I'm going to put G in parentheses. And this is a gas, so I'll put G in parentheses. Okay? Under normal conditions, water would be considered a liquid, so I'm using L. Please use a script L when you're doing the physical state. A capital L or little L's look like ones and I's, don't they? Capital I's, right? You can't tell whether it means one or the other, so please use a script L to mean a liquid, all right? And we've got symbols for G, which is gas, and you've got L, which means a liquid, S, which means a solid, and then we've got something called AQ, which means aqueous. And aqueous just means something is dissolved in water. Because we do a lot of equations in which we dissolve them in water. Do a lot of reactions in which we dissolve things in water. Now you don't know it, or might not know at this time, but this is going to be a gas. You'll find out in this unit how to predict when a hydrocarbon like this is a gas or a liquid or a solid. What physical state do we list after this one? Gas. Okay. How about this one? Yep, CO2 is a gas under normal conditions. Okay. And this one? You'd think it was a liquid, wouldn't you? Yeah, the problem is, and we'll find out more about this later, okay? This is a combustion reaction. We're burning a hydrocarbon, okay? Anytime you're reacting oxygen with a hydrocarbon, you will assume it to be burning, okay? And if we're burning it, that generates a lot of heat, right? Well, when you have water with a lot of heat, what physical state is that going to be? A gas. So in a combustion reaction, when water is a product, let's list that as a gas, okay? So you can do the physical states down here if I tell you this one's a gas, can't you? So write the physical states for those formulas there, all right? All right, so we're going to learn about 5 classifications of chemical reactions. The first category is synthesis. And synthesis just means putting things together. So this reaction here, I put together hydrogen and oxygen to make a more complex compound. That's a synthesis reaction. Okay? So that's a good example of a synthesis reaction. I'm going to leave a little space so you can put some more examples in there in a few minutes, okay? The opposite of synthesis is decomposition. Anybody got hydrogen peroxide in their medicine cabinet at home? What do you use that for? Huh? On burns?
No, I mean,
Cuts, scrapes, things like that? When you put hydrogen peroxide is always decomposing, okay? But when you put hydrogen peroxide on biological materials like blood, that catalyzes that reaction. It makes it go faster, okay? There's actually a better definition of what a catalyst is, but right now, going faster is fine, okay? So this stuff is actually dissolved in water. It's not a liquid. What you have on the bottle, usually says 3%. If you ever read the label on your hydrogen peroxide bottle, it says 3%. So it's 97% water. In fact, it's probably a lot less than 3%. By the time it gets to your medicine cabinet, it's probably about 1.5%. You're lucky if it's 2%. Because from the time it was manufactured, where it was 3%, the time it gets to the drugstore or grocery store or Walmart or whatever, it's already decomposed. Okay, the reason they put in those brown bottles is to try and keep it from decomposing as fast, because light catalyzes the reaction. It makes it happen a little faster. Okay, if you want to keep your hydrogen peroxide fresher longer, put it in the refrigerator. Keeping it cool will keep it from decomposing as fast. But most people don't keep it in their refrigerator, do they? That's where I keep mine, though. Okay? All right, so if I'm going to decompose that then, if I put it on a cut, and I put it around blood cells, they will cause that hydrogen peroxide to decompose. And it decomposes into water and oxygen. Okay, and what physical state do we assign to water? Liquid. What physical state do we assign to the oxygen? Huh? Gas. And that's where the bubbles come from. So when you put that on your cut and it starts to bubble, it's because you're generating oxygen. And what the oxygen does two things. One, that bubbling action flushes out any contaminants in the wound. But also, most of the bacteria that causes infections doesn't like oxygen. They're anaerobic. And so having that extra oxygen around that bacteria helps to get that, break it down or keep it from doing the damage that it would do. Okay, long enough for your cut to actually heal. And of course, the water just helps flush it out too. Okay, so this is a liquid, and this is a gas. And I want you to write an atom inventory and balance this equation, please. Everybody get what I got? Okay. So let's put that down as an example of decomposition then on your list up here, okay? Should be a plus sign, not an arrow. Okay. All right, then we've got combustion reactions, and we've already got two examples of that, because here are two hydrocarbons. There are lots of combustion reactions. Combustion reactions is technically is anything that you react with oxygen that in doing so produces both light and heat. It burns. That's a combustion reaction. I can burn iron. Okay, I can burn, let's see, well, everything else I'm thinking of here. Oh, hydrogen. Hydrogen, that can produce light and heat. The rocket that launched the Apollo space capsules to the moon, that used liquid hydrogen and liquid oxygen. So that was a combustion reaction. Now, we don't often think about it that way. So when that rocket went off, have you ever seen those videos with the big white clouds at the bottom? That was just water steam. That was actually, it was a condensing steam that was giving you the white cloud. Because steam itself you can't see. Steam is clear or transparent. So this could be a combustion reaction. It is a combustion reaction. We often don't think about it that way. Okay, it does produce light, but sometimes it's so little light you can't really see it. It's when you know for a fact that you've got light, then you have to identify it as a combustion reaction. These two definitely are combustion reactions. We're going to know that because we have a hydrocarbon and oxygen. For us, the only combustion reactions you're going to have to worry about are those in which you have a hydrocarbon reacting with oxygen. Okay? We don't list the light and heat and combustion reactions until we get to the thermochemistry unit. But these do produce products of light and heat. Okay? But let's list these as examples under combustion over here. Okay? So number 3 would be combustion. All right, number 4. Single replacement. In a single replacement reaction, some element by itself. Now that doesn't mean it can't be diatomic element like the hydrogen up here in that first equation we did. That's a diatomic element, okay? In its natural form and its most common environmental form is H2, and this is diatomic. It doesn't mean we can't have a single element that's diatomic, okay? I think sulfur is not natural element, the natural form is S6. So it doesn't mean that you don't have more than one, but that element by itself, okay? So in a single replacement reaction, an element by itself displaces, in fact, let's just change this, instead of replacement, let's call it displacement. Okay, single displacement. Okay, it displaces another element that it's like in a compound. In a single displacement reaction, an element displaces another element that it's like in a compound. Okay, in a single displacement reaction, an element displaces another element that it's like in a compound. Okay. So let's see here. How about we have magnesium. And we're going to put that into a solution with zinc chloride. What kind of an element is magnesium? Huh? I heard somebody say something. It's a solid. Okay. What else can we say about it? Where is it on the periodic table? Huh? It's one of the representative elements. What else can we say about it? Huh? Wants to give away electrons. Okay. What else can we say about it from where it is in the periodic table? Reviewing Unit 2. Regions of the periodic table. What else can we say about magnesium?
Oh, it's alkaline earth.
It is an alkaline earth metal, so it's one of those metals, isn't it? Okay. Except for two elements, all the metal elements or metallic elements tend to be solids. Okay, under normal conditions. Okay. What is the most commonly thought of liquid metal? Mercury. So there's one other metal that tends to be a liquid sometimes too, but magnesium is going to be a solid, and it's going to be a metal. Okay. Is there something in this compound then, based on those classifications, something in this compound that magnesium is like? Yeah, it's like zinc, at least when zinc's by itself, it's a metal element. It's an ion in this compound because it gave away those electrons you were talking about a moment ago. Okay? So, it's possible that zinc can displace, magnesium can displace zinc. Now, we'll find out a little later in this unit when you know it will happen. Okay? For right now, I'm just going to tell you it does happen. Okay? But it has to happen in the right environment. Because if I just take some magnesium metal and put it in with some solid zinc chloride, nothing's going to happen. I have to have this dissolved in water. Okay? And if it's dissolved in water, what physical state do we assign to it? Aqueous. Okay? Good. All right. So the magnesium is going to displace the zinc, which means it's going to join up with the chlorine. And it's going to kick the zinc out by itself. Well, a metal by itself, what's its physical state? Solid, because metals tend to be solids, don't they? Okay. This is in water here. Aqueous means it's in water. If this dissolves, it will also be aqueous, and I'm going to tell you up front that most chlorides, almost all chlorides, are going to be aqueous. Okay? Eventually, you'll be able to predict that. All right? But we have to balance the formula. What charge will magnesium have in a compound? Huh? What'd you say? 2 plus. Okay? That's right. What charge will chlorine have in a compound? -1. So, what do I need to do to balance this formula? Yeah, I have to have 2 chlorines. How do I write that to write a compound with 2 chlorines? Don't need a parentheses. A lowercase, a 2 down below here, a subscript 2. Okay? We only use parentheses if I have more than one polyatomic ion. The only time you write parentheses in a formula is when you have more than one polyatomic ion. So those polyatomic ions you were supposed to memorize for the last test, if you have more than one of those, you've got to put it in parentheses to write the formula correctly. Okay? That's only for the formula, not for the name. Okay? So this is how we start off figuring out the products. We'll get to that. Eventually, you're going to be able to predict these products. All right. So this is an example of a single displacement reaction then. I've got something that's by itself that's displacing something it's like in a compound. Does that make sense? A metal displacing a metal. All right? We need to balance the equation, though. So what are we going to use to balance an equation? Atom inventory. Okay. Yeah, you could call it atomic inventory, I guess, but we atom inventory. So balance the equation. Already balanced, wasn't it? Okay, but now you know for sure. Okay, you kind of kept up with, you got everything nice and organized, you know for certain that's that way. And I'm from Missouri, so you're showing me. Okay? All right. So that's a good example of a single displacement reaction. Let's put that in here in our list, okay? All right, let's see. Number 5, double replacement. And by the way, I used single replacement earlier. That's often used. I mean, you look on the internet or in textbooks, and a lot of times it's called single replacement. I prefer displacement only because that's what it does. It kicks something out, okay? And it's more descriptive of what's actually taking place. But this is called double replacement. All right, and we'll get more into when single displacement occurs and how to predict those and that sort of thing. Because eventually, if you're going to be given 2 reactants, you have to predict what the products are. Okay, and we'll show you how to do that. All right, a double replacement reaction then is a chemical reaction in which the front and back parts switch places. A double reaction is a reaction in which the front and back parts of 2 chemicals switch places. Okay? The front and back parts switch places. The front and back parts switch places. Okay. So if we look at these two compounds, if this is a double replacement reaction, then the front part of this is going to switch places with the front part of this. And the front part of this is going to switch places over here. So that this part goes with the back part here, and the front part goes with the back part. That makes sense? Okay? So calcium then is going to join up with the sulfur. So we're going through classifications of reactions. We've gone through a bunch of those already, but per your request, I've been recording all this, okay? So we're in double replacement right now, all right? So we've got calcium chloride and sodium sulfate, and both of these are listed as aqueous, which means what? They're dissolved in water, which gives it a pathway for a reaction to occur. In other words, the ions can move around a lot more easily in water. So the calcium is going to join up with the sulfate. Okay, and the sodium is going to join up with the chlorine. And now we've got to figure out how to balance the formulas over here. All right? Well, huh?
NaCl2.
Would it be NaCl2? Let's examine that for a minute. Because you can't, let me give you this little pithy saying, all right? Subscripts don't travel unless they're part of a polyatomic ion. Okay? Subscripts don't travel unless they're part of a polyatomic ion. So don't assume this 2 is automatically going to be over here. That's not the way things work. All right? What charge does a sodium ion have? +1. What charge? You've already answered this one already, so let somebody else do this one. What charge does a chlorine or chloride ion have? -1. So how many of each of these should we have here? One of each. Okay, so that's why that 2 can't travel over here. Does that make sense? You want to balance the formula. If I put a 2 there, the resulting compound would have a 1 negative charge. We don't want that. We want it to be balanced. Okay, so that's balanced 1 to 1. What charge does a calcium ion have? 2+. It's in column 2 of the periodic table. If you don't have out your periodic table looking at this and working along with me to figure this out, we're reinforcing what you should already know from Unit 2 here, okay? Elements in column 2 tend to have that 2+ charge. Actually, we talked about it, introduced it in 2. We actually went through it in a lot more detail in the last unit, Unit 4. So calcium has a 2+ charge, and you were supposed to memorize the charge on a sulfate ion. What charge does it have? -2. Okay, if you don't have those memorized, boy, you better go back and do that again, because you're going to need it from now on, well, from the last unit on, actually. So all those polyatomic ions you were supposed to memorize, you still got to have them. Okay, so this is a 2+, that's a 2 negative. That's balanced 1 to 1. Okay, the 2+ cancels out the 2 negative. It's balanced without having to write any more subscripts. All right. So then we need to identify its physical state. You wouldn't know it yet, but wait a minute. I'm sorry. That's actually going to be a solid. The sodium chloride is going to be an aqueous, but this is going to be a solid. So we'll write aqueous here. Okay? All right, so now we can balance the equation. All right, I'm going to let you balance the equation. Okay, you guys got what I got? Okay. Well, that's a good example of double replacement. Let's put that in our list over here, okay? What do you ask me to wait for? Huh? I can't hear more than one person at one time. What about sulfate?
It's one, it's like a thing by itself. It's a sulfate, it's not.
Oh, you wrote sulfate here instead of S and O? Oh, good, okay. So, what is this thing called right here? Atom inventory. Is it called an ion inventory? No. So you can't write SO4, all right? It's an atom inventory, all right? Now, let me explain why. Sometimes ion inventories work, but sometimes they don't, all right? And we're too early in your chemistry knowledge building process, okay, to know when you can use it and when you can't. The thing is that atom inventories work all the time. Ion inventories only work some of the time. Unless you know when you can use it, when you can't use an ion inventory. So always use an atom inventory, don't write it. In this case, if you wrote SO4, it would work, right? You got lucky, okay? But from now on, we want to write an atom inventory and not an ion inventory, okay? All right, so here's our example. All right. There's a subcategory under double replacement. These are the 5 major categories, but there's a subcategory for double replacement. So under 5, there's a 5A, okay? And this can be called a couple different things. It could be called acid-base, or neutralization. Now, I prefer acid-base, but there's a caveat here. If we have an acid-base reaction, you have to identify it by its major category and its subcategory, okay? If it's an acid-base reaction, you're going to identify it both as double replacement and acid-base, okay? So you get credit for both names, all right? You only get half credit if you only name it one thing. Got it? All right. Now, there's another thing that really won't become all that important until we get to the acids unit, and that is the kind of acid-base reaction. Right now, we're dealing with the simplest definitions of acids and bases, okay? And so all of these are going to be called, all these acids are known as Arrhenius acids, okay? Arrhenius acids and bases, ARRHENIUS, okay? What a pirate says, a female yardbird and you and I. Nobody's impressed, okay. All right. Okay. So the simplest definition of an acid. Those of you who had the naming for simple acids, okay, what did all the acids have in common? Hydrogen in the front of the formula, right? All right, so if all the acids we're talking about, the areneous acids, are going to have hydrogen in the front. I'm looking for my reference sheet. I put it down somewhere. There's a copy of it anyway. Let's do a real simple form of a simple acid. How about just HCl? Okay. And acids don't really do anything unless you put them in some kind of solution. And the only solution we're going to use, well, let me do this on a different sheet of paper because I should have put an A there instead of a Q. For us, all bases will have a hydroxide anion. For us, the areneous bases have to have a hydroxide ion, an hydroxide anion. And that's one of the polyatomic ions you're supposed to memorize. So what's the form of a hydroxide anion? What is it? What's its formula? OH negative, okay? So let's see, how about we had magnesium a while ago. We'll use Mg and 2 hydroxides to balance that out because it has a, well, I should be spaced there before I have the 2 here, okay? OH2, all right? And it's going to be, well, actually, let me see. OH, magnesium, we have that identified as being a solid in most cases, so we're going to call that a solid here. Okay. The thing about solids and aqueous in an aqueous environment, a water environment, is that everything dissolves. Everything dissolves a little bit or a lot. When we call it a solid like this in an aqueous environment, it means that most of it doesn't. It's mostly solid, okay? So it's like if you take sugar and you put it in water and you stir it up and you put some more sugar in water, you stir it up, eventually you get so much sugar in there it won't dissolve anymore, right? Don't you know that? You ever try to put too much sugar in your tea and it wouldn't, and it all sits at the bottom? Okay? Because we live in the South here, so we're talking about, iced tea. You know what happens, right? Now, if you heat up the water in sugar form what's called an azeotrope. So there technically is a point where you can dissolve all the sugar and you make a syrup. But table salt, there's a limit to how much you can dissolve that in water, and eventually it falls to the bottom. Well, some things dissolve a lot less than sugar or table salt. So when they dissolve a lot less, we call that a precipitate, even if it will dissolve some. Everything will dissolve to a greater or lesser degree. When we call it a precipitate or a solid in an aqueous environment like this, we mean that for the most part it doesn't dissolve, okay? So it's a relative term here. All right, so if we have an acid-base reaction, this is double replacement. The front part of this has got to join it with the back part of this, okay? The front part of this is hydrogen, and the back part of this is hydroxide. And the subscript doesn't travel because that 2 tells us I have 2 hydroxides. It's not part of the polyatomic ion. Well, what is that stuff? Well, look carefully. How many hydrogens are there? Huh? What'd you call it? 2 hydrogens, 1 oxygen? What do you call it? Somebody said something.
She said water.
Oh, good. I was trying to figure it out. I couldn't quite tell. When there's a couple people talking from up here, it's kind of seems a little bit confusing to me. And then we have our one person who has that accent that I have a hard time with anyway, so I apologize. So anyway, so that's water. Well, what physical state do we assign to water unless there's a lot of heat? Liquid. Okay. That's just another way to write water. In acid-base reactions, it's a lot easier to write it that way because then you can clearly see the front part went with the back part. That makes sense? So that's just water. Just another way of writing water we're showing clearly we put with a hydrogen ion with the hydroxide ion to make it. Okay? And the back part of this is going to go with this. What charge do we assign to the magnesium? What charge does magnesium have here? +2. How do you know that? It's in the second column. All the alkaline earth metals will have a 2+ charge in an ionic or a binary compound. And what charge does the chlorine have? -1, because it's a halogen, and all the elements in that column with the halogens have a 1 negative charge in a binary compound like this. So how many of each of those do I need to balance the formula? 1 and 2, okay, to balance the formula. And this is going to be aqueous. I think I told you that earlier about chloride compounds. They tend to be aqueous for the most part, okay? Well, now we got to balance the equation. This is an acid-base reaction because we're reacting an acid with a base. And what's happening is the acid is neutralizing the base, and the base is neutralizing the acid. So bases always neutralize acids, acids always neutralize base, hence the other name, neutralization. Okay? All right, so balance the equation. Okay, I thought I would go through this one with you just to make sure we're all kind of on the same page here. I've got 3 hydrogens on the left. Now you have to be careful here because I've got a hydrogen here and 2 hydrogens here. The 2 outside the parentheses multiplies everything inside. Since the hydroxide ion has 1 hydrogen, the 2 outside multiplies that by 2. That gives me 2 hydrogens here plus the 1 here. So I have 3 hydrogens to start with. I've got 1 chlorine, I've got 1 magnesium, and the 2 outside multiplies the 1 oxygen by 2. I got 2 oxygens on the left side. On the right side, I've got 2 hydrogens here, I've got 2 chlorines, I've got 1 magnesium, and I've got 1 oxygen. Okay? So if we're going to save hydrogen for next to last and oxygen last, we need to start with the chlorine. Okay, so I'll put a coefficient 2 right here to give me 2 chlorines to match those up. I'm going to automatically cancel out those. I'm going to put a, that means I have 2 hydrogens here now, plus the 2 here, that's 4, and I have 2 chlorines. Okay, if I go over to the other side then, I've got everything balanced but the hydrogens and the oxygens, and I want to save oxygen for last. So I want to balance hydrogen next to last. I'm ready to balance that. I'll put a coefficient 2 in front of the water in order to give me 4 hydrogens. I'm going to automatically go and cancel both those out because both those are found in that formula I just changed the number of by putting a coefficient there. And that's going to give me 4 hydrogens. Oh, I don't know why I marked out the chlorine. I should have marked out the oxygen down here. And I've got 2 of these. Okay? And so if you follow those steps that I gave you, save the oxygen for last, the hydrogen next to last, all of this works out, you know, a lot faster that way. So I'm just trying to give you a heads up on what it's going to take to balance equations a little bit faster, a little bit easier. Does that make sense? All right. How'd you do? Well, it wasn't as complex as I thought it was. Good. Let's write this down as our example then in our list of classification. All right? All right, so we have examples of all the types of equations, the classifications of equations we need. I want to write a general form for all of these. okay? Something that sort of defines what these types of equations are in a general way, okay? Since synthesis is always putting two things together to make something larger or more complex, we could say that's A plus B yields AB. Does that make sense? Well, if that's a general equation for synthesis, can you write a decomposition general equation? Come on, you can do this, right? Now, combustion is always going to be, for us anyway, is always going to be a hydrocarbon reacting with oxygen. So a hydrocarbon is made of carbons and hydrogens. What we don't know are the number of carbons and the number of hydrogens, okay? So I'm going to write subscripts of X and Y, okay? Some hydrocarbons are going to be gases, and some are going to be liquids, and some are going to be solids. So we also don't know what the physical state of our hydrocarbon is going to be. So I'm just going to put that down there as, let's just put a question mark for the moment. Okay, we don't know what the physical state's going to be. But we know it's always going to react with oxygen. And anytime you have a hydrocarbon reacting with oxygen, that oxygen is going to be in a gas form. And we're always producing the same products every time. Every time we're going to have CO2 that's going to be a gas, and we're going to have water. Because of the heat of a combustion reaction, the water is also going to be a gas. So that's our general form. That looks pretty specific. But for combustion reactions, we're always going to have that stuff. Now, what we don't know are the coefficients. Okay, so we don't know what this number is going to be here. Let's call that A and B and C and D, just to give it something there. Okay, we don't know what the coefficients are going to be. We know what the subscripts are going to be for most things, except for this. We don't know what that X and Y is going to be. Okay? So that's pretty specific, all right? And listen, you're going to have to be able to predict the products of a combustion reaction. But a combustion reaction is super easy to predict the products for because it's always exactly the same. It's always CO2 and water every time, all the time. If we have a hydrocarbon as our fuel and oxygen, it's always going to react with oxygen. That's what combustion is. So for us, at least, the predicting the products of a combustion reaction ought to be the easiest one to do. Okay? All right, single displacement. We've got to have something that's by itself. We can call that A. And some kind of compound, because there's got to be something in the compound that this thing that's by itself is like. We can call that BC. And since the thing that's by itself has got to displace the thing that is like, then the A is going to join up with C. And that means the B is going to be by itself. Now, because of time, we haven't gotten to the other kind of single displacement in which A displaces C. So in that case, we would have A, B, C, but now A is going to be on the back side. So now we're going to have BA plus C. Okay? We haven't covered that yet, but that can happen too. Okay? Double replacement. If this is AB, then what's this going to be? Come on, ABC. CD, because you got two parts, right? So A, B plus CD, and the front part is going to join with the back part of one going to the other. They're going to switch around. So what products are we going to have? What do you call it? AC. No, the front part's got to go with the back part. A, D, B, C. Right. And the front part always stays in the front. Okay? So it's going to be CB over here, okay? Always the front part stays in the front. The cations, the positively charged part of it, always stays in the front. Now, there are times when it might not be that way, but for us, anytime you're predicting them, it's going to come out this way. Okay? All right. Then let's look at our acid base. Okay? All acids have to have hydrogen in the front. So for our acid formula, we can call that Ha. Okay? Nobody's impressed with that either, huh? My chemistry jokes are falling flat today. For this class, they always fall flat. What's the deal with you? What's with you guys? Okay. And the bases for this class at this point in time always have to have hydroxide on the back side. Both. All right? And the front part's got to go with the back part. Front part's got to go with the back part. Okay, so that's a general form for an acid-base neutralization reaction, which is also double replacement because you have to name it both ways. That makes sense to everybody? Okay. How about I give you some equations to work on? Okay? So I'm going to give you some equations, and you are going to classify and balance these equations. You got it? Okay.
Is this homework?
Yep. Homework. Oop, I should have written that like this. If I don't put the physical states on there, it's because I expect you to be able to do that, okay? Did I do that one already? Is that the same one I gave you earlier? No, okay. Make sure I don't. But I did give you that compound earlier. let's see, let's give you one I haven't given you already. Let's look at what I've got here already. I had that one. Okay, so we'll make that a C4. H10. And it's still a gas. Okay, let's do.
Can you move it